I would like to report today on some of my recent work towards developing a new theory of quantum gravity, which I have called spontaneous quantum gravity. And one of the main achievements of the theory is to show how deeply the subject of quantum foundations is actually connected with the quantum gravity. So let's first talk about the theory of spontaneous collapse. This is a good criterion to say which physical theory is a good theory. So let's read it. If a physical theory agrees with some of the data, but not all the data, then it should be replaced by a falsifiable new theory which agrees with all the data. The new theory should reduce to the old theory in those domains where the old theory agrees with the data. So we have good examples of this in physics. For example, when we go from Newtonian mechanics to special relativity, this is how it works. Special relativity explains everything that classical mechanics does, and it explains more things which classical mechanics could not explain. So we call special relativity, let's say, to be the cover for Newtonian mechanics. Similarly, general relativity is a cover for Newtonian gravitation. It is a good transition. The new theory explains what the old theory did. It also explains things which the old theory could not explain. However, this criterion for a good physical theory fails when we go from Newtonian mechanics to quantum mechanics. I'll explain why that happens. Quantum mechanics works beautifully in the micro world, but it disagrees with the Newtonian mechanics. It was invented, quantum mechanics was invented to explain things which Newtonian mechanics does not explain. But in order to be a cover for classical mechanics, quantum mechanics should also have explained everything that classical mechanics does, but that's where QM fails. So we'll come to that. So we now need a new theory which agrees both with quantum mechanics and Newtonian mechanics. And in the sense that I just used the word cover, this new theory should be a cover for Newtonian mechanics, which for microscopic systems should reduce to quantum mechanics. So what's the problem? So at the heart of the disagreement between quantum mechanics and classical mechanics is the principle of quantum linear superposition. So what does the principle say? That suppose you have two states, say which are solutions of the Schrodinger equation, state A and state B. If the quantum system can be in state A, and if it can be in state B, then it can also be in a superposition. For example, that's what happens in the double slit interference experiment. The wave function can be the one which describes as if the electron went through the upper slit. It can also be the one as if the electron went through the lower slit, and then the superposed state is also a solution. That's why we see the interference pattern. Experimentally, the principle of quantum superposition has been verified for objects as heavy as up to 25,000 atomic mass units. That's made up of like this many nucleons. But we know from our daily life that quantum superposition fails for macroscopic objects. We don't see a large object like a chair to be in two positions at the same time. Unlike say for the electron, which can be in two places at the same time, a chair is never seen to be in two places at the same time. This contradicts quantum mechanics. Why? Because even though the Schrodinger equation seems to apply only for small objects, if you recall the mass that appears in the Schrodinger equation, that's arbitrary. It can be as large as we want. So the equations of quantum mechanics predicts that large objects should also be seen in superposed states, but we do not see that. And we can also ask, how is it that when we put a lot of atoms together, when each of these atoms obeys superposition, when we put a lot of them together, why is superposition lost? That's a good question to ask. So we are proposing that we need a new theory which goes to quantum mechanics for small objects, to classical mechanics for large objects, and explains how the same theory should explain how superposition is lost in the large mass limit. We should not have to have two theories. We should have just one theory, which is a cover for QM and Newtonian mechanics. Such a theory, in fact, was proposed in the 1980s by Girardi, Rimini, Weber, and Pearl. It is known as the theory of spontaneous collapse. So let us recall, in quantum mechanics, once a superposition has been created, it lasts forever because the Schrodinger equation is linear and it is deterministic. You prepare a superposition, it will stay that way. On the other hand, in classical mechanics, superpositions are not allowed at all. They are not observed. What the GRW theory of spontaneous collapse says is the following. Let's make a very, very small change to quantum mechanics. Namely, that the superposition of two states of a particle, say a proton, does not last forever, but only for an extremely long time, let's say t. T is the time for which the superposition lasts, and this proposed time they said to assume for a nucleon. For definiteness, let's say t for a nucleon, let's assume it's 10 to the power 17 seconds. So it's not infinite. The superposition lifetime for a two position states of a nucleon. So it's not infinite, but extremely large, in fact, of the order of the age of the universe. What happens after time t? GRW say, after time t, on the average, superposition spontaneously collapses to one or the other states from which the superposition was made. Like, so if the electron was here and there at the same time, then after a very long time, on its own, it will either collapse to here or there. So this is the theory of spontaneous collapse. It is not quantum mechanics. It's slightly different from quantum mechanics. But this little change suffices to provide the desired new theory which reduces to Newtonian mechanics for large objects. How? That's very straightforward. Consider an object, let's say, made with two particles, say a deuteron, which is a bound state, an entangled state of two nucleons. The superposition lifetime then becomes half, t by 2. Why? Because if the neutron undergoes spontaneous collapse, it will take the proton with it, say if we are talking of a deuteron. And if the proton undergoes a spontaneous collapse, it will take the deuteron with it. So the probability of spontaneous collapse doubles if you have an entangled state of two particles. So similarly, if you have three particles, it will be t by 3, t by 4. Now consider a macroscopic object which has n particles. N is huge, 10 to the 23, 10 to the 24. The superposition lifetime of an entangled state in an object made of n particles, the lifetime goes down to t by n. N is huge, you see. And even though t was enormous, it was 10 to the 17 seconds, t to the n is very small. If t is 10 to the 17 seconds, n is 10 to the 23, the superposition lifetime comes down to a millionth of a second. So if you have a chair and you try to make the chair in a superposition of two states, chair here and chair there, the superposed state will collapse in about a millionth of a second. That's why we don't perceive the superposition. So now you see this beautiful transition from quantum mechanics to Newtonian mechanics. Quantum superpositions don't last forever. They last for a very long time. In classical superpositions, it's not that they're absent, but they just last for an extremely short time. We don't see them. In that sense, the GRW theory of spontaneous collapse is a cover for Newtonian mechanics. It agrees with quantum mechanics for small systems, and it agrees with Newtonian mechanics for large systems, but in fact it is different from both QM and classical mechanics. It's falsifiable. It makes new predictions. You can see that this time parameter T is a new prediction of the theory. It's not a part. T is not there in either classical mechanics or in quantum mechanics. Experiments must test what the actual value of T is. The current experimental bound on T is that's greater than about 10 to the power 8 seconds. The GRW value is 10 to the 17. So there are still 9 orders of magnitude to go before GRW is ruled out. If experiments push T to larger than 10 to the 17 seconds, the theory is still ruled out, because if T is too large, then macroscopic superpositions will last for a long time. T by n will become much larger than a millionth of a second. We would see superpositions of a chair, and we don't. So 10 to the 17 seconds is the safest, the most conservative value you can give to this parameter T and still agree with classical mechanics. Okay. Spontaneous collapse is a very good idea, but there are also limitations. So there are limitations of this theory. Firstly, as a phenomenological theory, it's a very good theory. So it's testable, it's being tested, it's falsifiable. However, the criticism is that it is ad hoc. What is the origin of spontaneous collapse? What causes it? And what's the value of this T parameter? Where does it come from? So we'll see now that the GRW theory is very intimately connected to quantum gravity. Spontaneous collapse has its origin in quantum gravity. That's why the name spontaneous quantum gravity. We'll come to that. Furthermore, the GRW theory is non-relativistic. Attempts at making a Lorentz invariant collapse theory have not been successful. And in my opinion, we cannot have a relativistic collapse theory without additional inputs. The reason I think so is that in relativity, we need to treat time the same way as we treat space. So in the GRW theory, spontaneous collapse takes place only in position. Only the position operator gets localized to some particular eigenvalue. However, a relativistic theory of collapse, because it should treat time the same way as it treats space, should also have spontaneous collapse in time. This is very profound. So time has to become an operator so that spontaneous collapse in time can take. What does that mean? That the initial state can be a superposition of 2 times. In certain sense, electron can be simultaneously at 2 times, and then it collapses to 1 time or the other. That's spontaneous collapse in time. That should also be allowed in a relativistic theory of spontaneous collapse. Now, if time becomes an operator, how do we describe evolution? Turns out we need a new absolute time parameter, and as we'll see subsequently, this parameter comes from non-commutative geometry. So you already see that spontaneous collapse theory is guiding us towards quantum gravity, towards non-commutative geometry. Space and time both become operators. We are moving away from classical space-time. Okay, so let's now try to understand how we are guided to quantum gravity from this spontaneous collapse theory. And we see spontaneous collapse is essential if we are to sort of make quantum mechanics consistent with the classical mechanics. So we need spontaneous collapse. And we ask where the spontaneous collapse comes from. We are guided to understand that spontaneous collapse comes from quantum gravity. Uh, so talking about quantum gravity, there is no compelling experimental evidence that gravity should be quantized. However, there are reasons within quantum field theory which compel us to consider a non-classical nature for space-time. And the following is the logic. Time in quantum theory is part of a classical space-time geometry. Classical spacetime, in turn, is produced by classical bodies according to the laws of general relativity. I don't make a distinction between the spacetime manifold and the geometry on it. They come together. So classical spacetime geometry is produced by classical objects, but classical bodies are a limiting case of quantum systems. We should be able to describe quantum dynamics without classical systems. Yet Einstein's whole argument says that one cannot have a classical spacetime without classical objects. So you can see where we are headed. If quantum mechanics is to not depend on classical time, it should not depend on classical bodies, but classical bodies are needed to define a classical spacetime. It follows from there that we must have a formulation of quantum theory which does not depend on classical time. That is, there is a need to remove space-time from quantum field theory, and that is really a quantum theory of gravity. So we do not quantize gravity, we remove space-time from quantum theory. Okay, so if we want a formulation of quantum theory without space-time, can we arrive at it by quantizing classical gravity? The answer is no. Firstly, there is a logical reason for the answer being no. I mean, we could miss out something for the following reason. The rules of quantum theory were written down assuming space-time to be given. Now we are applying those very rules to remove space-time. This is illogical. Success is not guaranteed. We might miss out something. We'll see what we miss out, in fact. More seriously, if we arrive at quantum gravity by quantizing a classical theory of gravity, we will not be able to dynamically explain the absence of superposition of geometries in the classical limit. Same problem as in going from quantum to classical mechanics. You cannot explain the absence of position superpositions in classical systems if you start from quantum mechanics. Quantum mechanics predicts macroscopic superpositions, you don't see them. Same way, if you arrive at quantum gravity by quantizing classical gravity, the theory will predict superpositions of classical spacetime geometries, and those are not seen. Thus, to recover classical GR from quantum gravity, the sought for quantum gravity theory must admit spontaneous collapse of superposed geometries in the same spirit as the GRW theory. So that's why we call it spontaneous quantum gravity. Spontaneous quantum gravity explains the loss of superpositions of space-time geometries in the classical limit. It explains it dynamically in the same sense as GRW. Now, classical space, we agree, emerges from quantum gravity. It does not show superpositions. For classical space to exist without superpositions, macroscopic bodies must be classical. They should also not have superpositions. But large objects are made classical by the GRW theory. So you can see from this chain of logic that the GRW theory itself should originate from spontaneous quantum gravity, because quantum gravity, space emerges from quantum gravity. Space doesn't show superpositions. For space to not show superpositions, macroscopic objects should also not show superpositions, and that is ensured by the GRW theory. So there's a connection between spontaneous quantum gravity and GRW, and that is what we will build. We'll show where that connection is coming from. Okay. We have seen that for microscopic systems, GRW theory reduces to quantum theory. Similarly, we expect that for microscopic systems, spontaneous quantum gravity should reduce to quantum gravity. By quantum mechanics, we mean quantization of classical gravity. So we can say that the GRW theory is equal to quantum theory plus spontaneous collapse. Spontaneous collapse is what makes it classical. Similarly, spontaneous quantum gravity is equal to quantum gravity plus spontaneous collapse, where spontaneous collapse gives rise to the absence of superpositions of space-time geometries. It is this feature of spontaneous collapse which is missed out by conventional quantum gravity theories because they take quantum theory as given. So let's ask now, how can we make a mathematical formulation of spontaneous quantum gravity which admits GRW collapses? For that, we take help from what is known as the theory of trace dynamics developed by Stephen Adler and collaborators. So trace dynamics is a formalism that will guide us towards the sought for spontaneous quantum gravity. Trace dynamics derives quantum theory and spontaneous collapse both from an underlying pre-quantum matrix dynamics. Let me try to explain what that means. Trace dynamics is the dynamics of matrix models obeying a global unitary invariance and operating at the Planck scale. The theory assumes spacetime to be flat without gravity, Minkowski spacetime, but still it's assumed to operate at the Planck scale. So this is what we'll do. We'll add gravity to trace dynamics, but for that let's first describe what TD is. So quantum theory or quantum field theory is emergent as the statistical mechanics of these matrix models when they are coarse-grained over times much larger than Planck time. Okay, so what is the physics of trace dynamics? Instead of describing a point particle by a real number, suppose I choose to describe it by a matrix, by an operator. So I have a classical point particle, let's say in special relativity. We describe it by a real number. We write a Lagrangian for it, an action principle, equations of motion. So consider this example of a particle in a potential described by configuration variable q, having a Lagrangian q dot square minus q square. Integrate this over time. That is the action. What do we do in trace dynamics? We make this q into a matrix, into an operator. So the particle is now described by an operator. What is the Lagrangian now? This bold q shows the operator, or equivalently the matrix. Q dot means time derivative of every component of the matrix. Q dot square is the square of the matrix q dot minus q square. So this is now a matrix polynomial. How to make a scalar out of it which serves as a Lagrangian? Take its trace. Trace of this polynomial is the trace Lagrangian. Integrate it over time and we get the action. So this is how we make a transition from ordinary classical dynamics to what we call trace dynamics. We lift real number configuration variables to matrix configuration variables. These new configuration variables do not commute with each other. That's the essential property. So for example, if you had a set of matrix described particles, Q1, Q2 operators, they don't commute with each other. This is a Lagrangian dynamics. Given a Lagrangian, given an action, you can vary it with respect to the Q operators, get the Lagrange equations of motion. They are operator equations. You can also do this for fields by going to the continuum limit. Okay, the momenta also, which come from the Lagrangian, don't commute with each other. Nothing commutes. The Q's don't commute amongst each other, the P's don't, and the Q's and P's don't. So in that sense, matrix dynamics is more general than quantum mechanics. In quantum mechanics, you make the Q's and P's into operators, but you assign them the quantum commutation relations in terms of the Planck's constant. In matrix dynamics or in trace dynamics, there are no quantum commutation relations. The commutations are arbitrary. There's no Planck's constant. There's no Planck's constant in trace dynamics. Okay, these matrix elements are made from complex numbers and complex Grassmann numbers. The matrix elements of these trace dynamics matrices are made from complex Grassmann numbers. A complex Grassmann number is made from two real Grassmann numbers, and a Grassmann number is made from product of Grassmann elements. Grassmann elements anti-commute with each other. So if theta 1 and theta 2 are two such elements, then theta 1, theta 2 plus theta 2, theta 1 is 0. So clearly the square of a Grassmann element is also 0. A Grassmann matrix can be written as a sum of a bosonic matrix and a fermionic matrix. So if Q is a Grassmann matrix, we can write it as Q equals QB plus QF. A bosonic matrix is made from even grade Grassmann numbers. A even grade Grassmann number is 1, which is made from an even number of Grassmann elements, and it's easy to verify that even grade Grassmann elements commute with every other Grassmann element. A fermionic matrix is made from odd grade Grassmann elements, and the odd grade Grassmann number is made from an odd number product of Grassmann elements. Such numbers, odd grade Grassmann numbers, anti-commute with each other. So given any Grassmann number matrix, it can be written as the sum of a bosonic matrix and a fermionic matrix. These are used in quantum field theory. The bosonic matrices describe bosonic fields. Fermionic matrices describe fermion fields. So we make this split. We'll work with QB and QF. Now what about the dynamics? What about trace dynamics? You can write down Hamilton's equations of motion from the Lagrangian equations. You can construct generalized Poisson brackets. You can write equations of motion in terms of Poisson brackets. So dynamics works as before, as in classical dynamics, but the degrees of freedom are matrices. The trace Hamiltonian can be defined, it is conserved. Now what's new? What's new about matrix dynamics? There is a remarkable conserved charge which results from a global unitary invariance of the trace Lagrangian. Any Lagrangian, because it's a trace and because permutations are allowed inside the trace, matrices can be permuted without changing the trace. There is a global unitary invariance that the Lagrangian and Hamiltonian of trace dynamics have. As a consequence of that invariance, Noether's theorem tells us there is a very interesting conserved charge any trace dynamics will have. It's called the Adler-Miller charge, denoted in the literature by this symbol C tilde, and it is given by this equation. Take the bosonic matrices Qi bosonic, find out the commutator Qi pi, and sum it over all the bosonic degrees of freedom, and from that subtract the QI/PI anti-commutator for all the fermionic degrees of freedom. So sigma Bi QI/PI minus sigma Fi QI/PI anti-commutator. This is conserved. This is a quantity which has the dimensions of action. So there's no Planck's constant in trace dynamics, but there is this conserved charge with dimensions of action, which plays a very central role in the theory. In fact, this is responsible for the emergence of quantum theory from trace dynamics. As you can see, there's no analog of this in point particle mechanics. In ordinary Newtonian mechanics, C tilde would be trivially zero if you replace Q's and P's by real numbers. So this charge, let's remember, the Adler-Miller charge, is very crucial. Okay. So trace dynamics resembles matrix models as they have been studied in quantum field theory and string theory, except that we do not quantize this trace dynamics. In the usual study of matrix models, in the usual study of matrix models, they are quantized, they are subjected to canonical quantization. We don't do that. In fact, we want quantum theory out of trace time. We want it to emerge. So how is that done? TD is supposed to operate at the Planck scale. We average it over Planck times. We coarse grain it using the methods of statistical mechanics. We coarse grain it over Planck times. And the mean emergent dynamics working on time scales larger than Planck scale is quantum dynamics. So quantum dynamics is emergent from trace dynamics, and clearly then the laws of mechanics on the Planck scale are not those of quantum field theory, but rather those of trace dynamics. Quantum field theory is emergent. Conventionally, we apply statistical mechanics to derive properties of macroscopic systems from atomic theory. But here in trace dynamics, statistical mechanics is applied to find the time average dynamics over scales larger than Planck time. So consider an ensemble of a large number of systems in phase space, each of which obeys trace dynamics. Let us find the equilibrium ensemble after coarse graining, subject to requiring that the trace Hamiltonian and the Adler-Miller charge are conserved. So in usual statistical mechanics, we impose the condition, let's say, that the energy may be conserved. Here we impose the condition that the trace Hamiltonian and the Adler-Miller charge are conserved. And then we do statistical mechanics in the conventional way. We define a measure on the phase space in trace dynamics. We prove Liouville's theorem, namely that volumes are conserved during evolution. We define a density distribution function in the phase space, and we can define the Boltzmann entropy, and we maximize this entropy to find out what is the equilibrium state when we have coarse grain over time intervals much larger than Planck, which is the same thing as saying that we want to know what's the dynamics at energy scales much lower than Planck energy scale. So at the Planck energy scale, the dynamics is trace dynamics. But when you come to lower scales, we find, using these methods, that the Adler-Miller charge gets equipartition. So remember the form that the charge had. It is equipartition, and for every degree of freedom, it has the same value, which we now identify with Planck's constant, because it's equal for all the charges, all degrees of freedom. So in this sense, Planck's constant emerges after doing the statistical thermodynamics in TD. When that is done, also quantum commutation relations emerge. The C tilde, the Adler-Miller charge, has been equipartition. Each commutator is equal to IH bar, and as a consequence of the fact that the underlying theory obeys Hamilton's equations of motion, the averaged canonical variables, after doing the stat-mech, they obey the standard quantum Heisenberg equations of motion. From here, one can transform to the Schrodinger picture and can also construct the standard quantum field theory from this emergent theory. So the takeaway message is that quantum field theory is a statistical approximation to the underlying trace dynamics which is operating on the Planck scale. Okay. Next, what is the connection between trace dynamics and spontaneous collapse? What's the connection with the GRW theory? So as we saw, quantum dynamics is the equilibrium approximation of trace dynamics. Quantum theory is an emergent phenomenon. Now, under certain circumstances, if many of these degrees of freedom get entangled, like a chair was an entangled state of many nucleons, in the same sense, if many of these Q matrices get entangled with each other, fluctuations around equilibrium can become important. This will become clearer when we talk of spontaneous quantum gravity. So the point is that up till now we have neglected statistical fluctuations. We have looked only at equilibrium. It turns out that if many particles are entangled with each other, these fluctuations can become important. And then if the trace Hamiltonian picks up a significant imaginary part, anti-self-adjoint correction, then quantum mechanics, the equilibrium approximation, breaks down and spontaneous localization results. So let's look at that a little slowly. Spontaneous quantum gravity will show us that a particular anti-self-adjoint correction to the Hamiltonian of the theory becomes important if a large number of these matrices are in an entangled state. And that gives rise to a very rapid spontaneous localization, a breakdown of quantum theory. So trace dynamics is then a cover for classical dynamics as well as quantum mechanics, and it is an underlying theory which removes the ad hocness of GRW. So when these so-called Brownian motion fluctuations around equilibrium are important, trace dynamics reduces to classical mechanics, moving away from the quantum theory which had emerged at equilibrium. So we can say trace dynamics is equal to quantum theory plus spontaneous collapse, just as in the GRW theory. So in this sense, trace dynamics explains GRW as emergent when fluctuations around equilibrium are important, but the TD doesn't specify any Lagrangian for the theory. See, Lagrangian is not given, only the formalism is given. So we don't know where this anti-Hermitian part to the Hamiltonian is coming from. We'll see that when we include gravity. So you recall there is no gravity in trace dynamics. The space-time part is Minkowski, it's flat. We now take a clue from the structure of trace dynamics to understand how to utilize non-commutative geometry to include gravity into trace dynamics, and this leads us to the theory of spontaneous quantum gravity. Okay, so spontaneous quantum gravity is in a sense a unification of Adler's trace dynamics program with Alan Cohn's non-commutative geometry program. We cannot add gravity to trace dynamics simply using general relativity. We have to describe the gravitational degrees of freedom now as operators. So if we have a metric in classical spacetime, every component of the metric has to be now made an operator. We need a matrix type description of gravity. Also, that should not be tied up to quantum theory. We're trying to derive quantum theory. We cannot say take the metric and make it into an operator like one would do in a canonical quantization. Not that either. So we seek a matrix dynamics description for matter plus gravity on the Planck scale. Matter part we have seen, TD does that. How to do that for gravity. And we also require that whatever we do to make this spontaneous quantum gravity theory or this matrix dynamics, from there quantum gravity and spontaneous localization should emerge after coarse graining over Planck times. So just as we saw in trace dynamics, that what did we see in trace dynamics? That you do the statistical mechanics and you get as emergent quantum theory, and you get spontaneous collapse as resulting from fluctuations. You want to get the same thing out after doing the statmex of this matrix dynamics for matter plus gravity. We should get quantum gravity at equilibrium. And for large systems, spontaneous fluctuations should become important, giving rise to loss of superposition of spacetime geometries. We can motivate the need for non-commutative geometry like this. In TD, in trace dynamics, material particles were raised to the status of matrices. So every point particle is described by a matrix. We want to do the same thing for space-time points. So particles, matter itself, material objects are described by real numbers. Those are replaced by matrices. Every space-time point now also has to be replaced by a matrix, by an operator. Space-time point becomes an operator. And beautifully, that is exactly what non-commutative geometry does. That's shown in this cartoon at the bottom. You take ordinary geometry, Euclidean or Riemannian geometry. We know that a geometry can be mapped to an algebra, a commutative algebra, which in a sense is equivalent to the geometry. It describes the geometry in algebraic terms. Now we take this algebra, we make it to non-commutative. And namely, for example, if we had functions, ordinary functions of real numbers in this commutative algebra, you make those functions, suppose you had, let's say, real number variables, you change them into matrices which will no longer commute. So your algebra has become non-commutative. And then we can ask this question, which is the geometry which this non-commutative algebra describes? And that's what we call a non-commutative geometry. It turns out that all the essential features of a geometry, say distance, metric, curvature, they can all be now contained in this non-commutative algebra. In terms of the language of this non-commutative algebra, we describe all the standard features of ordinary geometry, say Riemannian geometry. From the physical viewpoint of a theory, a physical theory, this is what happens. Let's look at the left part of this cartoon. Classical general relativity describes how matter produces Riemannian geometry. So material particles plus the geometry of space-time together are described by the laws of classical general relativity. How do we make a transition to matrix dynamics? Go to the right. Material particles are to be replaced by matrices. For now, we deal only with fermions, matter fermions. We leave the case of gauge fields for future. Riemannian geometry becomes a non-commutative geometry, and it's inevitable then that classical general relativity is raised to spontaneous quantum gravity. This is what happens. So you see the map from classical GR in the non-commutative case is precisely the theory of spontaneous quantum gravity. If you take the statistical mechanics, if you perform the statistical mechanics of the spontaneous quantum gravity, then the equilibrium emergent theory is quantum gravity. If fluctuations are important, then spontaneous collapse takes place, and spontaneous collapse takes us to classical general relativity. I hope you see this picture. Just like the GRW theory for small masses is quantum mechanics, when the masses become macroscopic, GRW reduces to classical mechanics. Same way, spontaneous quantum gravity reduces to quantum gravity in the micro world and to classical general relativity in the macro world. Okay, so space-time point structure is lost in non-commutative geometry. So we lose space, we lose time. We don't have time to describe, time is not there in NCG. How to describe evolution? Interestingly, it turns out that non-commutative geometries come with their own new absolute time parameter. I don't have time to go into this. We call this the Cohn's time tau. That's a notation I use. So when we work with NCG, we don't have a space-time, but we have a bookkeeping fundamental time parameter. Okay, so just as we raised matter to material points to the status of matrices in trace dynamics, we now raise space-time geometry to the status of operators. How do we do that? So we will assume that what was the space-time geometry, the metric, has to be now not the metric by itself, but conceptually gravity will be described by a bosonic Grassmann operator. How do we do that? Luckily, NCG gives us a clue. There is a beautiful result in the theory, namely that the Dirac operator dB on Riemannian geometry, the usual Dirac operator I gamma mu grad mu, given a Riemannian spacetime manifold which is curved, which has curvature, take the Dirac operator dB on that space, square it, take its trace. The sum of the eigenvalues of the square of the Dirac operator is the Einstein-Hilbert action for that space. And this is an incredible and beautiful result which is central to our further development. So the information about the curvature, the Ricci scalar on that space-time is encoded in the trace of dB squares. Now dB is an operator, in the same spirit as in operators are needed in matrix dynamics. This Dirac operator describes curvature also in non-commutative geometry. So when you go to NCG, you have lost your space-time. There is no d4x, there is no root g in the sense it's there in Riemannian geometry. But because you have coded the information about curvature in an operator, namely the Dirac operator, we have now a description of curvature in NCG in terms of this Dirac operator. So how to make contact with the trace dynamics? Introduce a new gravity operator. We call that QB. QB is defined such that the time derivative of QB is the Dirac operator dB. I hope you get the picture. dB came to us from Riemannian geometry, but we now use it in NCG also. And QB, the so-called gravity bosonic Grassmann operator. QB is a bosonic Grassmann matrix. It is defined such that QB dot is dB. And that straight away gives us a hint for how to describe the action principle for gravity in this matrix gravity, which will link to trace dynamics. That's like we do in TD. QB dot square, that is like a velocity trace of that. So this is a matrix. Take its matrix trace, integrate it over time. So there you have the gravity action trace q dot square d tau. It's very natural, except that we have to remember that QB is a matrix and we have to take the trace of QB dot square. So this is the action principle for gravity in our matrix dynamics. What about matter? We would like to introduce matter into the theory. So that's a fermionic matter. We denote it by this operator QF. Now we could say that we could write a matter Lagrangian for each fermion. From that we could get the stress energy tensor for all the QFs together and couple that to the gravity action that we have just seen. But there are various reasons for which we don't go down on that path. Essentially, let's ask this question. What is the gravitational field of an electron? Say, now, electron described by a quantum wave function in a sense is spread all over space. If the electron is all over space and its gravity is also all over space, we would not like to make a distinction between the electron and its gravity. We don't want to distinguish between a fermion and the gravitational field it produces. So we introduce a new concept of an atom of space-time matter. So we denote it by the symbol Q. Also, if we ask what is the gravitational field of an electron, the electron is this operator QF. Its gravitational field is QB. So we define the new operator Q equals QB plus QF. QF, since it describes a fermion, is a Grassmann operator, and this separation into QB plus QF is essentially like saying that if you take any Grassmann operator Q, you can write it as its sum of its bosonic and fermionic parts. So this is the definition of an atom of space-time matter. An electron together with its gravitational field is a STM atom. If you take another object, say a quark, that's also an STM atom, so long as you describe it along with its gravitational effect. So it turns out that with every STM atom, we'll associate a length scale L. That's all. No mass, no spin, just a length scale L. And the full Dirac operator will be D equals dB plus dF, where dF is defined by dQf by d tau, and d is equal to dQb by d tau plus dQf by d tau. So this is the full Dirac operator. It's a bosonic part and a fermionic part, dF. The fermionic Dirac operator is not self-adjoint. The bosonic Dirac operator is self-adjoint, but dF, there's no restriction. It has a self-adjoint and anti-self-adjoint part, and it is what causes spontaneous localization. It is constructed in such a way that dF will reduce to the matter part of Einstein equations in the classical limit. dB, we have already seen, is related to the Einstein-Hilbert action. dF is related to the matter part of the Einstein-Hilbert action. So what is the action principle for matrix dynamics of STM atoms? So we added the matter part. So take the operator ds. So earlier it was trace dB square, yeah, for pure gravity. Now you take trace di square for the ith atom, sum it over all atoms, integrate over tau. This is the fundamental action principle for the matrix dynamics of STM atoms. Okay, this is it. We've got now the Lagrangian and the action for describing spontaneous quantum gravity. So this is the action. It is nice. It looks very simple, and turns out that this action contains quantum gravity. It contains quantum theory, and it contains classical general relativity in it, all as emergent phenomena. It's quite a powerful action. It has a lot of information, although it looks very simple. Now, given this matrix dynamics action, which is a generalization of trace dynamics, which now includes gravity, we can repeat the trace dynamics analysis. We can do statistical mechanics with it. There are only two fundamental constants in matrix dynamics gravity. One is Planck length, one is Planck time. Then this theory, as before, has a conserved Adler-Miller charge. And with every STM atom, we have an associated length scale L, which of course can be different for different STM atoms. So there is no Planck mass in this theory. There is no Planck's constant h bar. There is no Newton's constant g. All of that will emerge. So this is the structure of matrix dynamics gravity. Okay, this diagram summarizes the dynamics that emerges from this matrix dynamics of STM. So level 0, so we call this the 4 levels of gravitational dynamics. Level 0 is where the trace dynamics of STM atoms takes place. If we do the statistical thermodynamics of STM atoms by making a canonical ensemble, then the equilibrium theory is quantum gravity. Remember earlier the equilibrium theory was quantum theory, now it is quantum gravity. If fluctuations away from equilibrium become significant, we'll come to that in a moment, then the equilibrium approximation breaks down, spontaneous localization takes place, and what emerges is classical space-time, which is classical general relativity with matter source. So that's level 3. So level 1 is the statistical theory, that is quantum gravity or away from equilibrium spontaneous localization. From there you get level 3, that is classicality. Those STM atoms which have not undergone spontaneous collapse, they stay at level 0, but you can describe it at level 1, or even more approximately, you can ignore their gravity part QB. You can take space-time from level 3, QF from level 0 or level 1, and you can make this hybrid level, level 2, which is where we do all our quantum theory. Quantum fields on a classical curved space-time is done by taking quantum matter fields from level 1 and classical space-time from level 3. So this is spontaneous quantum gravity is operating at level 0. This I just repeat what I said. You can go through it once again. At level 0, we have a Hilbert space on which STM atoms live, no space-time. So level 0 is really a Hilbert space from which space-time emerges. Space-time and laws of general relativity emerge at level 3 after spontaneous localization. And because QB is described by a bosonic operator, turns out since it is adjoint, self-adjoint, it does not undergo spontaneous localization. Only the fermionic part of an STM atom localizes. The bosonic part does not. And so these localized fermionic parts is what give rise to space-time. So statistical thermodynamics of level 0 atoms gives rise to quantum gravity at equilibrium at level 1 below Planck's. That you remember. The coarse graining has been done over length scales much larger than Planck time. Standard quantum commutation relations for fermionic and bosonic part, as well as the Heisenberg equations of motion, these emerge at level 1. Cohn's time is still present. And yet remember, quantum gravity now is a low energy phenomenon. It's not happening at the Planck scale. Planck scale is the spontaneous quantum gravity, but just ordinary quantum gravity, in the sense of quantization of a classical gravity, this comes into play whenever background spacetime is not available. Level 1 quantum gravity is also the sought after description of quantum theory without classical spacetime. Okay. Planck's constant and Newton's gravitational constant emerge at level 1. The mass of an STM atom is inverse of its length L, because now we have h bar. We can define mass as h bar by mc. That allows us to interpret L as the Compton wavelength, the Compton length of an STM atom. If a sufficiently many STM atoms get entangled with each other, their effective Compton wavelength goes below Planck length. Because, if the total mass goes above Planck mass, the effective wavelength comes below Planck length. The approximation that we made, that we can coarse grain the level 0 Planck scale dynamics, that breaks down. If the effective Compton wavelength goes below Planck length, we cannot coarse grain over Planck times or Planck length scales. Fluctuations taking place at the Planck scale become important. An anti-self-adjoint part from the fermionic Hamiltonian is no longer negligible, and the entangled system undergoes rapid spontaneous localization. So spontaneous collapse happens when you entangle a large number of STM atoms, because as a consequence of this large number entanglement, an anti-self-adjoint part which was earlier negligible now becomes crucial for the fermionic part, and fermions undergo localization. The localization of the fermionic part of many such entangled systems gives rise to macroscopic bodies of the universe. Their bosonic parts together describe classical gravity, which obeys GR. Those STM atoms which do not undergo spontaneous collapse are described at level 0 or level 1, or at the hybrid level 2. The theory of spontaneous quantum gravity makes the following predictions. It predicts the GRW3. GRW is a consequence of spontaneous localization. It predicts quantum interference in time, spontaneous collapse in time. It predicts that a certain length known as the Karo-Lihasi length is the minimum length scale one can measure with the instrument. This is something testable in the laboratory in principle. Then the spontaneous quantum gravity predicts dark energy as a quantum gravitational phenomenon. It also provides an explanation for black hole entropy from the microstates of STM atoms. So finally, we can say that spontaneous quantum gravity explains the emergence of the classical world from quantum gravity without having to resort to any interpretation of quantum mechanics. So thank you for listening.